Hi, welcome to iEducator. This is Teacher Jeff. I'm an educator and an engineer by profession. And today we will discuss Chapter 2. And Chapter 2 is all about linear programming models or the resource allocation models. And in this lesson, there are 5 key areas that I'm going to be highlighting right now. First is the introduction of linear programming models. Second, I will be discussing as well the properties of linear programming models. Third, the maximization models. Fourth, the minimization models. And finally, the methods used in solving linear programming models. Right now, we will discuss the first key area, which is the introduction to linear programming models. So what is meant by linear programming? In linear programming, it is a mathematical technique for finding the best uses of an organization's resources. This means that this is the technique that helps managers whenever they want to allocate the available limited resources for various competing activities for achieving their desired objective. We need to understand that every business organization has two objectives. First is to maximize the profits, and second is to minimize the cost. Okay. Second, linear programming has been defined as a method of dealing with decision problems that can be expressed as constrained linear models. This is quite difficult to comprehend, but what it means is that linear programming is one of the most versatile, powerful, and useful technique for making management decisions. And as a decision-making tool, it has demonstrated its value in various fields. It can be applied in production, where you are trying to maximize your profits and at the same time minimize the cost of your raw materials. It can also be applied in finance, in marketing, in research and development, and even in personal management aspects. And lastly, linear programming is defined or is used to find minimum cost, maximum profits, maximum amount of earning that can take place under a given condition. Now, we know for a fact that the objective of each business enterprise, like I said earlier, is to make a profit, right? Now, in order to do that, we should be a customer-centered, we should be a customer-oriented organization. What I mean about that is that we should involve our customers in the manufacture of our product. And how are we supposed to do that? Simply, we need to collect the voice of our customers, or the VOC. The voice of our customers may include customers' inquiries, customer complaints, customer suggestions, etc. And then we need to translate it into some kind of customer specifications and to make sure that the organization is able to meet these specifications or requirements to achieve customer satisfaction. Right now, we will also discuss the properties of linear programming models. And there are 4 properties that I'm going to discuss to you today. The first property is the relationship between variables and constraints must be linear. Second, the model must have objective function. Third, the model must have structural constraints. And lastly, the model must have non-negative constraints. Now, in order for us to better understand what these properties really mean, let us discuss first the different terminologies used in linear programming. Now, one of the terminologies that we normally use, that would be decision variables. When we say decision variables, this refers to mathematical symbols representing levels of activity of a firm. So it can be the variables A and B. It can be the variables x and y, or it can be x sub 1, x sub 2, or y sub 1, y sub 2, okay? These are mathematical symbols. Moving on, we have constraints. And when we say constraints, these are requirements or restrictions placed on the firm by the operating environment stated in the linear relationships of the decision variables. Now, there are two types of constraints. First, we have structural explicit or non-negativity, or also known as the implicit constraint. When we say structural or explicit constraint, it refers to a limit on the availability of resources. For example, under production department, let's just say the capacity of our machine, that would be 40 machine hours. So therefore, we should not exceed on 40 hours, because that's the only availability, the limitations of the capacity of our machine. So that's what we call structural or explicit constraint. And when we say non-negativity, it restricts or variables to 0 or positive. So for non-negativity, the numbers or the quantities should not be in negative form. It can either be equal to 0 or it can either be higher than 0. But we will discuss this one further in order for us to better understand what really structural or non-negativity constraints are. Another terms that we normally use in linear programming, that would be the objective function. Objective function is a linear mathematical relationship describing an objective of the firm in terms of decision variables. In linear programming, we are normally faced with two decisions. It's either we maximize the profit or we minimize the cost. So that's normally the objectives of the firm. Parameters, on the other hand, these are numerical coefficients and constants used in the objective function and constraints. And aside from that, we have feasible region. This is a set of combination of values for the decision variables that satisfy the non-negatively conditions and all the constraints simultaneously. That is the allowable decisions. Now, as you can see on the figure presented at the left portion, you have their feasible region. So that is where it is located. And aside from that, we have two lines intersecting each other. So below that line or below that those lines, the boundary, that would be our physical region. And we also have what we call extreme point. Extreme point is the corner of the feasible region. If a linear programming problem has a solution, then there is always at least one extreme point solution, okay? And optimal solution, this is a combination of decision variable amounts that yield the best possible value of the objective function and satisfy all the constraints. So as long as it satisfies all the constraints, then we have what we call optimal solution. And when we say multiple optimal solution, the condition in which a linear programming has more than one optimal solution. And if we say infeasibility, this is the case where there is no feasible solution which satisfies all constraints, or there are no points that satisfy all constraints. So if there is something that has been not followed, or if there is something that is not being satisfied, then we call that one as infeasibility. When I say not being satisfied, I'm referring to the constraints, okay? We also have what we call redundancy. Redundancy is a constraint which does not affect the feasible region. As you can see on the presented figure, you have their redundant constraint, okay? That is presented in some sort of a vertical line. And as you can notice, it does not affect our physical or feasible region. And when we say unbounded, This is the condition when the objective function of a linear programming problem can be infinitely large without violating any of our constraints. As you can see, our feasible region is very infinitely large, okay? And now, in order for us to better understand these terminologies of linear programming, let's have an example. So our example states a company manufactures two products. We have product X and product Y, which require the following resources. The resources are the capacities of machines. So in this particular example, we have three machineries. We have machine 1, machine 2, and machine 3. The available capacities are 50, 25, and 15 hours, respectively, in the planning period. Your product X requires 1 hour of machine 2 and 1 hour of machine 3. And your product Y requires 2 hours of machine 1, 2 hours of machine 2, and 1 hour of machine 3. And the profit contribution of X and Y products are $5 and $4 respectively. Now, since we are presented with these data or pieces of information, we have technically collected our data already. And once we are done with data collection, what we need to do next is to analyze our data. There are a couple of ways to analyze our data. It can be through tabulations or graphical forms, but for this matter, we will make use of tabulation. We will tabulate the data given in order for us to better understand, for better comprehension. So as you can see, the contents of the statement can be summarized as follows. So I've made 3 columns. You have columns for your machine, a column for your products, and a column for your availability of your machines in terms of hours. Remember that we have 3 different machines: machine 1, machine 2, and machine 3. And also, you have 2 different products. You have product X and product Y, and the availability of your machines as well. Availability meaning these are the capacities of your 3 different machines. So for machine 1, you have 50 hours, machine 2, 25, and machine 3, you have 15 hours. Now, with respect to product X, remember that your product X does not need machine 1. It only requires machines 2 and 3. So for machine 2, it requires 1 hour. And for machine 3, it also requires 1 hour with a profit of $5 per unit. And for product Y, it requires all 3 machines. So for the first machine, it requires 2 hours, 2 hours for machine 2 and 1 hour for machine 3. And remember that its profit margin is $4 per unit. Now, how do we solve this type of problem? Now, in solving this type of problem, we need to strictly follow these model formulation steps. Now, the reason we need to follow these is for us to be guided, for us to be directed in properly answering the problem scenario. Now, the first model formulation step that we need to do is to clearly define the decision variables. Second, we need to construct the objective function. And lastly, we need to formulate the constraints. Now, let's have step 1 first. It says, clearly define the decision variables. Remember that in our terminologies, we have defined decision variables which refer to mathematical symbols, right? So as you can notice here in our problem states a company manufactures 2 products, X and Y. So apparently, our decision variables, that would be product X and product Y, or it can be brand X or brand Y if you're comfortable using that, okay? again, our decision variables, that would be product X and product Y. Now, based on our problem, it is already apparent that our two decision variables are your product X and Y. After defining our decision variables, the next step we need to do is to construct the objective function. Now, in order to do that, in constructing the objective function, we need to go back first to our tabulation for us to be having a good visual on the information. Now, as you can see, machine capacities are available resources, right? Profit contribution of the products X and Y are also given. We have $5 and $4 respectively. Now, having this information, the question now is, are we now able to formulate the model? Yes, we actually are. But how do we do that? In order to do that, let the company manufactures X units of product X and Y units of product Y, as the profit contribution of products X and Y are $5 and $4 respectively. So it is very clear now that the objective of the problem is to maximize profits, okay? So how do we write that one? So in order to write that one, we may say maximize Z equals 5x plus 4y, where Z refers to your profit per day, where 5 refers to your profits of your product X, and 4 refers to your profit margin to your product Y. Okay? So that's the decision of the company. They need to maximize their profit. So therefore, we are finally done with step number 2. And after constructing the objective function, the last step that we need to do is to formulate the constraints. Now, how do we do that? In doing that, let's move on first, or let's go back rather, to our tabulation for a better visual. Now, in order to formulate the constraints, again, as defined earlier, constraints refer to the requirements or restrictions placed on the firm by the operating environment stated in the linear relationships of the decision variables. And so going back, we need to consider the utilization of our machine hours. So how many machines do we have again? We have 3. Now, as you can see, each machine has its corresponding capacity. For machine 1, we have a capacity of 50 hours. Machine 2 has 25 hours. And finally, machine 3 has 15 hours. This being considered, the utilization of machine hours by product X and product Y should not exceed the available capacity. So our linear structural constraint, that should be this one. So this is how it looks like, okay? So we have to create 3 linear structural constraints. Why 3? Because we have 3 machines. So with respect to machine 1, so our first linear structural constraint, that would be 0x plus 2y less than or equal to 50. Because if we try to go back to our tabulation as to how we come up with those numbers and constants, okay, going back, there. So as you can see, it should be 0x with respect to machine 1. So our first linear structure, that would be 0x plus 2y less than or equal to 50 hours. Why did we use an inequality of less than or equal to 50 hours? Remember, the reason is because we are trying to maximize the profit. However, the condition is we should not exceed from our capacity, and our capacity is 50 hours. So that is why we make use of less than or equal to inequality. And our second linear structural constraint, that would be 1x plus 2y less than or equal to 25. And lastly, for machine 3, our linear structural constraint that would be 1x plus 1y less than or equal to 15. Now that we have formulated our constraint, so what's next? Well, actually, we're not done yet. We are not done yet because we also need to consider that the company may decide either to stop the production of products X and Y, or they may also decide to manufacture any amount of products X and Y. So remember, supposing you are the company and you are trying to decide not to produce any amount of product, that means to say that there is no production. So the quantity of your products, that would be equal to 0. On the other hand, if you decide to produce or manufacture any amount of products X and Y, so therefore the quantity of your products would be greater than 0. So that is now non-negativity constraint comes in. So our non-negativity constraint should be written as X is greater than or equal to 0. Y is greater than or equal to 0, or it can be also written as X and Y greater than or equal to 0, or it can be both X and Y are greater than or equal to 0. Now, as you can see, as the problem has got objective function, structural constraints and non-negativity constraints, and there existing a linear relationship between the variables and the constraints in the form of inequalities, the problem then satisfies the properties of the linear programming problem. However, there are also basic assumptions for this particular problem, and I will be discussing the 7 basic assumptions. Now, the first assumption that we have, it is assumed that the decision maker here is completely certain. When we say completely certain, he or she is in deterministic condition regarding all aspects of the situation. May it be about the availability of resources, the profit contribution of products, the technology or the machineries and equipment used, the courses of action taken, and their consequences, okay? That's our first assumption. The second assumption, it is assumed that the relationship between variables in the problem and the resources available or the constraints of the problem exhibit linearity. Here, the term linearity implies proportionality or additivity. This assumption is very useful as it simplifies modeling of the problem. And the third basic assumption that we have, we assume here fixed technology. What do we mean by that? When we say fixed technology, we are actually referring to the fact that the production requirements are fixed during the planning period. And the fourth one, it is assumed that the profit contribution of a product remains constant irrespective of level of production and sales. When we say remains constant, it doesn't change regardless whether or not you add the production of your products X and Y, or you deduct or you lessen the production of your X and Y. It's still the same. It's still fixed, okay? And the fifth one, it is assumed that the decision variables are continuous. If we say continuous, it means that companies manufacture products in fractional units. For example, company manufactures 2.5 vehicles or 3.2 barrels of oil, etc. This is also referred to as the assumption of divisibility. Okay, that's what continuous mean. For number 6 assumption, it is assumed that only one decision is required for the planning period. For this one, this condition shows that the linear programming model is a static model, which implies that linear programming problem is a single-stage decision problem. On the other hand, dynamic programming problem is a multi-stage decision problem. And finally, the last assumption that would be all variables are restricted to non-negative values, or their numerical value will be greater than or equal to 0. Okay. The next key area that I'm going to be discussing right now, that would be the maximization model. Okay, so in this model, or in this key area, we're going to be highlighting, we're going to be further discussing as to how to maximize the company's profit. Now, in order to better understand maximization models, this is best understood by giving an example. So, for example, so this is how our problem looks like. And this is an example of a maximization problem. And our example, that would be a product mix problem, a Beaver Creek Pottery Company. Now, how many bowls and mugs should be produced to maximize profits given labor and materials constraints? And product resource requirements and unit profit are as follows. So as you can see on our tabulation presented, okay, this is a tabulation of our resource requirements. And as you can notice, this is composed of 4 columns. First column, we have our product column. Second, we have our labor, which is expressed in terms of our per units. The third column refers to our clay, which is expressed in terms of pounds per unit. And the last column refers to our profit column, which is expressed in dollars per unit. Now, as you can see on the first column, in our product column, we have 2 products, right? So as you can see in our problem, we have our bowls and we have our mugs. So we have product 1 and product 2. In terms of bowl, the resource requirement in terms of labor, that would be 1 hour per unit, okay? So per bowl, that will be manufactured in an hour. In terms of clay, we're gonna be needing 4 pounds per bowl, okay? And for the profits of a bowl product, that would be $40 per bowl. On the other hand, for the mug, it's going to be manufactured for 2 hours per unit or per mug. That would be in terms of labor. On the other hand, in terms of clay, we're gonna be needing 3 pounds per unit, and the profit, that would be $50 per mug. And as you can notice as well, to answer this particular problem, let us consider the following additional capacity information. As you can notice in the bottom part of our tabulation, our resource is 40 hours of labor per day. And our availability is 120 pounds of clay. In order to properly solve this problem, we need to strictly follow our model formulation steps. And remember, our step 1 in solving the problem is to clearly define our decision variables, okay? And if you can recall in our terminologies which are normally used in linear programming problems, one of those is decision variables, and decision variables refer to mathematical symbols. Now, since based on our problem, we have 2 products involved, we have the bowl and the mug. Now, in this case, our decision variables are x sub 1, which refers to the number of bowls to produce per day. And we also have x sub 2, which refers to the number of mugs to produce per day. Or if you're not comfortable using variables x sub 1 and x sub 2, you can simply use variables a and b, or perhaps variables x and y depending on your own preferences. But in this case, I would just have to use x sub 1 and x sub 2 as my decision variables. Now, if you have already clearly defined your decision variables, the second step in solving this problem is to construct our objective function. So in order to do that, let me go back first to our tabulation in order for us to have a proper view of the problem. Now, if you can notice in our tabulation presented, labor and clay capacities are our available resources. Profit contribution of products x sub 1 and x sub 2 are also given. Now, with this information, we are now able to formulate the model. And in order to do that, we should let the company manufacture x sub 1 units of product x sub 1 and x sub 2 units of product x sub 2, as the product contributions of products x sub 1 and x sub 2 are $40 and $50 respectively. So therefore, our objective variable, so that would be is to maximize Z equals $40 times x sub 1 plus $50 times x sub 2, where Z refers to your profit per day, right? So as we go back to our tabulation, so this is how we did it. So as you can notice in our tabulation presented, so Z equals $40. Remember that Z refers to your profit. And our formula is maximize $40 times x sub 1. And x sub 1 is your bowl, right? So $40 is adjacent to your product x sub 1 or bowl. And plus $50 times x sub 2. And x sub 2 refers to your mug. So that is how we construct our objective function. And remember that if we say objective function, you need to remember that there are only two objectives that a company has. First is either to maximize the profit, and second is to minimize the cost. So in this case, this particular problem is an example of maximizing our profit. Okay, the next step that we need to do, okay, after constructing our objective function, it is then imperative to do our final step, which is to formulate our constraints. And how do we do that? Okay, in formulating the constraints, as you can see in our tabulation above, in order to formulate our constraints, we need to consider two things. First, we need to consider the utilization of our labor hours, which in this case, that would be 40 hours of labor per day. Second, we also need to consider the utilization of our clay capacity, which is in this case, that's going to be 120 pounds of clay. Remember, we only have two products, correct? We have product X sub 1 and product X sub 2. Now, the utilization of labor hours and the weight of the clay should not exceed our available capacity. Again, I would like to reiterate, the utilization of labor hours and the weight of clay should not exceed the available capacity. And therefore, our linear structural constraints should be, first, you have 1 times x sub 1 plus 2 times x sub 2 less than or equal to 40 hours of labor. And our second linear structural constraint, that would be 4 times x sub 1 plus 3 times x sub 2 less than or equal to 120 hours of clay. However, we also need to consider the fact that the company may either decide to stop the production of both products or may decide to manufacture any amount of both products. The final constraint to be formulated is then the non-negativity constraint. Our non-negativity, and that would be x sub 1 greater than or equal to 0, x sub 2 greater than or equal to 0, or it can be written as x sub 1 comma x sub 2 greater than or equal to 0, or it can also be written as both x sub 1 and x sub 2 are greater than or equal to 0. Now, this means that if the company decides to stop the production of both products, then the quantity of both products is 0, right? So that would be equal to 0. Or if the company decides to manufacture any amount of both products, then the quantity of both products will be greater than 0. Okay? Now, during our discussion on the terminologies that are commonly used in linear programming problem, one of the terminologies that would be a feasible solution or feasibility. So when we say a feasible solution, it does not violate any of our constraints. Now, for example, in step number 1, we have decision variables. Remember, we have two products. We have your bowls, which refers to your x sub 1, and we have your mugs as well, which refers to your x sub 2. Now, in this case, let us suppose that we have produced 5 bowls. And for x sub 2, let's suppose that we have produced 10 mugs. Now, step number 2, our objective function, remember, that would be to maximize z equals $40 times x sub 1 plus $50 times x sub 2. Now, since our x sub 1 and x sub 2 values are given, so all we need to do is to plug in the values to our formula. So that would be $40 times 5 plus $50 times 10. So that would be equal to z equals $200 plus $500. And therefore, our z or profit, that would become $700. And step number 3, how will we create our labor constraints and clay constraints? Because we have two different linear structural constraints. First, we have labor and we have clay constraints as well. Now, for our labor constraints, that would be 1 times x sub 1 plus 2 times x sub 2 less than or equal to 40 hours of labor. And let's see if this is feasible, okay? So all we need to do is to plug in the values of our decision variables x sub 1 and x sub 2. So that would be 1 times 5 plus 2 times 10. So 1 times 5, that would be 5. And 2 times 10, that would be 20. So a total of 25 hours. Is 25 hours less than or equal to 40 hours? 25 hours is less than 40 hours. And therefore, since we have not exceed with our constraint, or since we have not exceed with our capacity 40 hours, therefore, this is considered as feasible solution because we did not violate any of our constraint. We did not violate our labor constraint, to be specific. Now, let's try to calculate whether or not we violate our clay constraint. Now, remember, our inequality under clay constraint, that would be 4 times x sub 1 plus 3 times x sub 2 less than or equal to 120 pounds of clay. And remember, we should not exceed with our capacity 120 pounds so that it will be considered as feasible. So all we need to do again is to plug in the values to our formula. So that would be 4 times 5 plus 3 times 10. So 4 times 5, that's 20, plus 3 times 10, that's 30. So 40 plus 30, that would be 70 pounds. So question, is 70 pounds less than or equal to 120 pounds? Yes, 70 pounds is less than 120 pounds, and therefore, this is considered as a feasible solution because we did not violate our clay constraint. But what about there is a violation? Or can we give an example of infeasible solution? Yes, we actually can. So this is now an example of an infeasible solution. When we say infeasible solution, it violates at least one of the constraints. So let's see if there is a violation later on. Okay, step number 1, decision variables. So our given x sub 1, that would be equal to 10 balls, assuming, and our x sub 2, that would be 20 months. Now, our objective function, that would be the same. To maximize our profit z equals $40 times x sub 1 plus $50 times x sub 2. So all we need to do is to, again, plug in the values to our formula. So $40 times 10 plus $50 times 20. So that would be 400 plus 1,000, and therefore our z would be equal to $1,400 or $1,400. So step 3, let us try to see if there is a violation. So let's have our labor constraint. And our labor constraint inequality, that would be 1 times x sub 1 plus 2 times x sub 2 less than or equal to 40 hours of labor. So since we already have the values of our x sub 1 and x sub 2 respectively, we will plug this into our formula. So 1 times 10 plus 2 times 20 less than or equal to 40 hours of labor. Now 1 times 10 is equal to 10. 2 times 20, that's equal to 40. And therefore, 10 plus 40 is equal to 50. Now question, is 50 less than or equal to 40 hours of labor? Okay, 50 hours is greater than 40 hours of labor, and therefore, since it exceeded our maximum capacity, which is 40 hours, this is infeasible because it violates at least one of our constraints. Okay, and the next key area that I'm gonna be highlighting right now, that would be minimization problem. Now, in order for us to better understand minimization problem, this can be best understood by giving an example. Okay, for example, 2 brands of fertilizer available. So we have Super-gro and Crop-quick. The field requires at least 16 pounds of nitrogen and 24 pounds of phosphate. On the other hand, Super-gro costs $6 per bag and Crop-quick costs $3 per bag. Now problem, how much of each brand to purchase to minimize total cost of fertilizer given the following data? Okay, in the earlier problem, that was an example of maximization, meaning to say we are trying to maximize our profit. Now in this particular problem, this is an example of minimization problem wherein we are trying to minimize the cost, and so for that matter, we will ask ourselves how much of each brand to purchase to minimize total cost of fertilizer given the following data. Okay, as you can see on the tabulation presented, this is our tabulation for our chemical contribution. And our tabulation is composed of 4 columns. You have your brand, nitrogen, which is expressed in terms of pounds per bag. You also have your phosphate, which is expressed in terms of pounds per bag as well. And you have your cost, which is expressed in terms of dollars per bag. Now for your Super-gro, which is our x sub 1, or our first decision variable, so we're gonna be needing 2 pounds per bag of nitrogen and 4 pounds per bag of phosphate, and the cost, that would be $6 per bag. On the other hand, for Crop-quick, which is our x sub 2 or our second decision variable, we're gonna be needing 4 pounds per bag of nitrogen and 3 pounds per bag of phosphate. And the cost, that would be $3 per bag. Now, what's our constraints? Now, as you can notice, under nitrogen, it should be greater than or equal to 16 pounds. Okay, so that's our first constraint. And second, under phosphate, it should be greater than or equal to 24 pounds. Okay, remember that in properly solving the said problem, we need to strictly follow our formulation steps. And step number 1, we need to clearly define our decision variables. And so for this matter, our X sub 1 refers to the bags of Super-gro, and our X sub 2 refers to the bags of Crop-quick. So in this case, our decision variables are the variables X sub 1 and X sub 2. Now, after clearly defining our decision variables, the next step that we're going to be needing to do is to construct the objective function. Again, in this case, we're trying to minimize the cost. So going back to our tabulation, see on the tabulation presented, you have there your last column, which is your cost, right? Your Super-gro costs $6 per bag, and your Crop-quick costs $3 per bag, and your Super-gro is expressed in X sub 1, and your Crop-quick is expressed in X sub 2. And so therefore, if we state our step number 2, constructing the objective function, it should be stated minimize Z equals $6 times X sub 1 plus $3 times X sub 2, where $6 X sub 1 refers to the cost of bags of Super-gro, and $3 X sub 2 refers to the bags of Crop-quick, and Z refers to your cost. After constructing our objective function, the last step that we're going to be needing to do is to formulate now our constraints. Now, are we now able to formulate our constraints? Yes, we are actually now able to formulate our constraints. Now, in order for us to better formulate our constraints, let us refer to the tabulation given above. Okay. Under constraints 16 pounds of nitrogen, okay, in the second column of the tabulation above, you have their nitrogen, and therefore, if we construct or formulate our first linear structural constraints, so that would be 2 times X sub 1 plus 4 times X sub 2 greater than or equal to 16 pounds, okay? So that would be our first linear structural constraints. Now, in terms of our 24 pounds of phosphate constraints, so our second linear structural constraint, that would be 4 times X sub 1 plus 3 times X sub 2 greater than or equal to 24 pounds. Finally, our non-negativity constraint, that would be X sub 1 greater than or equal to 0, X sub 2 greater than or equal to 0, or it can be written as X sub 1, comma, X sub 2 greater than or equal to 0. Or also, it can be written as both X sub 1 and X sub 2 are greater than or equal to 0. Now, and finally, the last key area that I'm going to be highlighting right now, that would be the methods used in solving linear programming problems. Now, take note, we are already aware that linear programming is a method of solving the type of problem in which 2 or more candidates or activities are competing to utilize the available limited resources with a view to optimize the objective function of the problem. Now, the objective may either be to maximize the returns or profits or to minimize the cost. Now, there are actually various methods that are used to solve linear programming model. And what are these methods in solving linear programming problems. Now, the first method in solving linear programming problem, that would be the graphical method. If we say graphical method, it is employed when we only have two decision variables in the problem. Now, to deal with more decision variables by graphical method, it will become more complicated because we have to deal with planes instead of straight lines. And therefore, in graphical method, let us limit ourselves to two variable problems only. And the second method used in solving linear programming problem, that would be the simplex method. If we say simplex method, it is the most powerful method to solve linear programming problems when the problem is having more than two decision variables. Now, this means that it has a systematic program which can be used to solve the problem. And the third method used in solving linear programming problems, that would be the systematic trial and error method. This is where we go on giving various values to variables until we get optimal solution. And because of that, this method takes much of time and very laborious, and therefore this method is not discussed here in this chapter. And finally, the last method used in solving linear programming problems, that would be the vector method. And in this method, each decision variable is considered as a vector, and as principles of vector algebra is used to get the optimal solution. Now, like the systematic trial and error method, this method is also time-consuming, and that is why it is not discussed here. So these are all the methods that are normally used in solving linear programming problems. First, we have the graphical. Next, we have the simplex. Third, we have the systematic trial and error method. And lastly, we have the vector method. And so for this matter, let us discuss first the graphical method. Now, in graphical method, the inequalities or structural constraints are considered to be equations. Again, I would like to reiterate, in graphical method, the inequalities or structural constraints are considered to be equations. This is because one cannot draw a graph for inequality, right? Instead, graphs can only be drawn using equation. And so for that matter, only two variable problems are considered. Again, we are only using two variables because we can draw straight lines in two-dimensional plane. And if we say two-dimensional plane, it refers to x-axis and y-axis. Moreover, as we have non-negativity constraint in the problem, that is all the decision variables must have positive values. Always, the solution to the problem lies in the first quadrant of our graph. But we may be asking ourselves, has there been a time that the value of variables fall in different quadrant? The answer is yes. Sometimes, the value of variables may fail in quadrant other than the first quadrant. So what do we do then if that happens? Well, in such cases, the line joining the values of the variables must be extended into the first quadrant. The procedure of the method will be explained in detail while solving a numerical problem. Now, the characteristics of a graphical method, that would be first, generally, the method is used to solve the problem when it involves two decision variables. Second, for three or more decision variables, the graph deals with planes and requires high imagination to identify the solution area. Third, always the solution to the problem lies in the first quadrant, like I said earlier. And lastly, this method provides a basis for understanding the other method of solution. Now, in order for us to better understand how to solve linear programming problem, applying the graphical method. So let us have an example. Now, in this example, I'm going to be solving linear programming problem by applying graphical method. And before solving the problem, let me explain to you first the basic concepts of linear programming problem. Now, as discussed in the earliest parts of our lesson, we learned that linear programming is a mathematical technique for finding the best uses of an organization's resources. And also, we learned that every business organization has two objectives. First, maximization, or maximizing the profit of the company. And second, minimization, or minimizing the total cost of production. And so for that matter, with the help of the linear programming problem, graphical method, it will allow us to find the optimum solution. Remember, there are different methods in solving linear programming problem. We have graphical method, we have the simplex method, we have the systematic trial and error method, and the vector method as well. Now, since both the systematic trial and error method and the vector method respectively are time-consuming, they are not feasible to use in solving linear programming problem. And because of that, aside from graphical and simplex methods, the other methods that are available for use are, first, dual simplex method, and second, we have the Bingham method. And take note that graphical method is only applicable if we only have two variables involved. Now, if we have more than two variables, then the graphical method is not suitable to be used. Now, as you can notice, there are three models of graphical methods presented. First is the maximization model with two linear structural constraints. Second is minimization problem, which has two linear structural constraints. And finally, the last model, we have maximization model with three linear structural constraints. So in this case, I'm going to explain three different models of graphical method. Right now, I will only be highlighting the first model, which is the maximization model with only two linear structural constraints. And so let us first solve the first model, which is maximization model with two linear structural constraints. So this is our problem. Again, this is a linear programming model applying graphical methods. Now our problem, solve the following linear programming problem using the graphical method. Maximize z equals 17 times x sub 1 plus 21 x sub 1, where z refers to our profit, and subject to 15 times x sub 1 plus 25 times x sub 2 less than or equal to 125. So that is our first linear structural constraint. And our second linear structural constraint, that would be 13 times x sub 1 plus 13 times x sub 2 less than or equal to 85. And our non-negativity constraint, that would be x sub 1 and x sub 2 is greater than or equal to 0. Now in this problem, we need to find the value of our x sub 1 and x sub 2. And the value of these variables should be greater than or equal to 0, which means positive values only. Now, in order to solve a linear programming model using graphical method, the first thing that we need to do is to convert our first linear structural constraint into an equation. So the one highlighted, so that would be our first linear structural constraint. Since that is expressed in inequality, therefore we cannot make graphical presentation to that. And so for that matter, we will convert that one into an equation. our first equation under solution, that would be 15x sub 1 plus 25x sub 2 equals 125. So this is our first equation. So what's next? Next, we need to find the value of our x sub 1 and x sub 2. And in doing that, we need points to plot our graph sheet. Hence, in order to identify our 2 points, let us take a look at the first constraint and find the boundary conditions. Then what is the value of our x sub 2? Here, remember that we have already converted our first linear structural constraint into an equation, and that becomes 15x sub 1 plus 25x sub 2 equals 125. When x sub 1 is equal to 0, so what is the value of x sub 2? So all we need to do is to plug in this value to our formula. And so 15 times 0 plus 25x sub 2 equals 125. 15 times 0, that's 0. So it's canceled out. So therefore, x sub 2 is equal to 125 all over 25. So the value of our x sub 2, that will be 5. Okay? So we now have a value of our x sub 1 and x sub 2. Next, supposing the value of our x sub 2 is 0. So what is the value of our x sub 1? And so for that matter, remember that our equation is 15x sub 1 plus 25x sub 2 equals 25. So by plugging in the values to our formula, so 15x sub 1 plus 25 times 0 equals 125, and x sub 1 equals 125 all over 15. So the value of our x sub 1, that would be 8.33 units. Okay? So next, the next thing that we need to do is to plot our points. Remember, our first point is 0 and 5. As you can notice, this is our graphical sheet. The horizontal line, that would be our x sub 1 axis, and our vertical line, that would be our x sub 2 axis. Now, as you can notice, our x sub 1 is 0, and our x sub 2 is 5, right? Now, if we are trying to plot that one, so that is located there. As you can see, highlighted in green, so that would be our point 0.05. Is to put our second point to our graphical sheet. So our second point is 8.33 for x sub 1 and 0 for x sub 2. So if you can notice, our x-axis, that would be our x sub 1, and our y-axis, that would be our x sub 2. As you can notice, our horizontal line, that would be our x sub 1 axis, and our vertical line, that would be our x sub 2 axis. Remember, your x sub 1 is 8.33, so that is located there, and your x sub 2 is 0. You can see, this line represents our first constraint, which is 15x sub 1 plus 25x sub 2 less than or equal to 125. Now, the next thing we need to do is to find or plot our second line. Now, going back to our constraint, okay, the next thing that we need to do is to plot our second line. And in order to do that, we need to make use of our second linear structural constraint. Since we are now done with the first linear structural constraint, this is now time for us to make use of our second linear structural constraint, okay, for our second line. So our second linear structural constraint, that would be 13x sub 1 plus 13x sub 2 less than or equal to 85. And remember, the first thing that we need to do is to convert this one into an equation. So converting that one into an equation, so solution, that becomes 13x sub 1 plus 13x sub 2 equals 85. So when x sub 1 is equal to 0, what is then the value of our x sub 2? Because the second thing that we need to do is to find the values of our x sub 1 and x sub 2. Now, in order to do that, all we need to do is to plug in the value to our formula. So that becomes 13 times 0 plus 13 x sub 2 less than or equal to 85. So x sub 2 equals 85 all over 13. So the value of our x sub 2 is 6.54. Okay, so we have then the first point. Our x sub 1 is 0 and our x sub 2 is 6.54. Next is to find our second point in order for us to be able to draw a line. So in order to do that, let's assume that our x sub 2 is equal to 0. So we need to find the value of our x sub 1. So in order to do that, all we need to do is to plug in the value of our x sub 2 to our formula. And that becomes 13 x sub 1 plus 13 times 0 equals 85. So x sub 1 equals 85 all over 13. So the value of our x sub 1, that will be 6.54. Okay, so we already have found the values of our x sub 1 and x sub 2. So we can now plot these to our graph sheet. So remember, you have there 0.06.54. So if we plot that one into our graph sheet, that is where it is located. Okay, and the second point, we have 6.540, and that is where our located. Now, this line represents our second linear structural constraint, which is 13x sub 1 plus 13x sub 2 equals 85. Now, the next thing that we need to do is to combine both lines. So combining both lines, this is how it looks like, okay? Now, after combining our two lines, the third step that we need to do is to find our feasible region. So where do you think our feasible region would be located? Now, remember, as defined earlier, if we say feasible region, it refers to the set of combination of values for the decision variables that satisfy the non-negatively conditions and all the constraints simultaneously. That is the allowable decision. Now, in order to find the feasible region, just take a look at the two constraints. Just check whether it is less than or equal to, or greater than or equal to, because based on that, we will be able to find the feasible region. Now, as you can see, our first constraint, the inequality we are using is less than or equal to. Same with our second constraint. And so for this matter, we need to find the feasible region, and our feasible region should be below the line which we have drawn in our graph sheet. And our feasible region should be below our two lines. Also, as you can see, our feasible region has 4 corners. Now, in the earliest part of our discussion, in the terminologies that are commonly used in solving linear programming problem, these 4 corners refer to our extreme points. Remember, extreme points refer to the corner of the feasible region. If a linear programming problem has a solution, there is always at least one extreme point solution. And so for that matter, we need to find the value of our 4 corners. So what is the value of A? So we have there corner A, corner B, corner C, and corner D. Now the value of our A, or corner A, is 0, 0. The value of our corner B, that would be 6.540. The value of our letter C, or corner C rather, approximately 4.25, 2.75, and the value of our corner D, or extreme point D, that would be 0.5. Now, the last step that we need to do is to substitute these values to our objective function. Okay, here, Let us substitute first the value of our extreme point A or corner A. Remember, our corner A values, that would be 0, 0. Now, in substituting that to our objective function, which is maximize z equals 17x sub 1 plus 25x sub 2. Now, all we need to do is to plug in the values of our extreme point A, 0, 0. So 17 times 0 plus 21 times 0, that would be equal to 0. Next is to substitute the values of our extreme point B. So 17 times 6.54 plus 21 times 0 equals 111.18. Substituting the values of our extreme point C, so that would be equal to 17 times 4.25 plus 21 times 2.75. So that would be 130. And lastly, substituting the value of our extreme point D, that would be 17 times 0 plus 25 times 5, that would be 105. Now remember that in extreme point definition, it says, if a linear programming problem has a solution, there is always at least one extreme point. So in this case, basing on the values of our 4 extreme points, we need to select the one that has the highest value. And as you can notice, the extreme point that has the highest value is the extreme point C, which is $130. And so for that matter, that will be our final answer. All right, I think that's a good place to stop. If you have questions, please let me know on the comment section. And if you like this video, please don't forget to subscribe and hit the bell button for the latest updates. Thank you.